Hi guys, so in this video we're going to be taking a look at the effect of bypass or decoupling capacitors on the as implemented on the 555 timer circuit. This specific circuit has been configured to generate a 38 kilohertz square wave with a duty cycle of about 50%, and we're going to be using this circuit eventually in an infrared repeater transmitter. However, today we're just going to be having a look at the effect of the capacitors. We're going to be having a look at the current consumption of this chip, specifically as the chip transitions from one level to another. That's normally when you have the current spikes on the supply rail. So let's have a look at the circuit diagram, just a rough circuit diagram, and see how we have configured this specific chip configuration. Now here's the basic circuit as we have it set up on the breadboard. I didn't draw in all the components on this 555 timer chip. Suffice to say, this chip is in an astable configuration. It's set up to oscillate at 38 kilohertz at about 50% duty cycle. Okay, so we're feeding it 5 volts, measuring the output of the chip over here on pin 3, and then over here we've got that 0.1 ohm Vichy shunt resistor that we spoke about, and then these are the two decoupling capacitors that we will be testing, removing from the circuit to see what the effects are on the current consumption as well as on the output of the waveform from this oscillator. Okay, let's go and have a look. Alright, so here we have the circuit viewed from the top. This of course is the 555 timer circuit, and what we're going to be doing is we're going to be measuring the output of the 555 timer circuit over here, and we're going to be having a look at the power rail, what the voltage spikes or dips looks like on the power rail. I have over here a 100 nanofarad capacitor that should filter out any of the high frequency spikes, and then over here we've got the 47 microfarad large value electrolytic capacitor, and we will be unplugging them into the circuit and having a look at what the output looks like and what the power rail looks like as well. We will also be measuring the circuit. We will also be measuring the power consumption of the circuit using a 0.1 ohm shunt resistor. It's a Vichy 1% 0.1 ohm shunt resistor over here. We're just going to be measuring the voltage drop over that resistor in order to measure the current consumption of the circuit. Alright, let's go and have a look at what it looks like. So here's the basic circuit. I'm driving it at 5 volt DC, as you can see there on the multimeter. Just measuring from the power supply over there. I've got this shunt resistor over here. We'll be measuring the voltage drop over that soon. Let's just check the output frequency of this 555 timer circuit. Set it to right, and there we can see it's more or less 38 kilohertz, which is exactly what we want for some future projects. Let's go and have a look what the output waveform looks like on the oscilloscope. I've got the oscilloscope set to 2 volts per division. Now let's connect up the output of the 555 timer circuit, which I have on this probe. There you go. You can see I've already set the trigger level, and it's triggering on the positive going edge. Now let's add the power rail, which I've got on this probe here. Just turn on that channel. Okay. And you can see I've got that set to 2 volts per division as well. Now the ground plane for channel 2 is over here. So you can see it's measuring the 5 volt DC level over there. What you should also be able to see if you're viewing this in HD is these tiny little glitches that coincide with the positive going edge of the 555 timer right over there. Okay, so what we want to do is zoom in on those little glitches. So we're going to be changing the channel 2 input to AC coupling, and just increasing the vertical sensitivity. There we go. Okay, so you can see there we're now at 200 millivolts per division for channel 2, and you can see the power dips are at more or less 200 millivolts. Alright, so the spikes that you're seeing there, the 200 millivolt drop in the on the power rail, is in fact with the 47 microfarad capacitor and the 100 nanofarad capacitor in play. So I mean, if we just have a look and zoom in on that, you can see, you know, it's a fair amount of drop already. Let's remove the 47 microfarad capacitor from the circuit. Right, let me disconnect it. There we go. Now you can see that the voltage drop is more significant and more pronounced with the 47 microfarad capacitor removed. Now let's also remove the 100 nanofarad capacitor and see what happens. Wow, okay, you can see there's a massive amount of additional noise being introduced into the circuit. Let's just quickly zoom back out and also reduce the vertical sensitivity on channel 2 here. Right, okay, so you can see there at channel 2, on channel 2 we at 2 volts per division again, right? So you can see this power spike is more than 2 volts on the positive going side and more than 2 volts on the negative going side. What we've also seen here now is we've got this spike on the output of the NE555 timer circuit being added. You can see things are starting to really get bad. Okay, so let's I'm going to plug the 47 microfarad capacitor back in. You can see it's already filtering out most of that noise. You can see the spikes are still there with the positive going edges. If we just increase the vertical sensitivity again, right, and if we add back the 100 nanofarad capacitor, it almost gets rid of the last of the high frequency noise on the power rail. Okay, so you can see very important that that we add some bypass capacitors on the 555 timer circuit, else it's going to introduce quite a lot of noise into the rest of your circuit. So let's just add the 0.1 ohm shunt resistor into the circuit. We're just going to be measuring the voltage drop across that resistor now and see what it looks like on the oscilloscope. So what you're looking at there is the voltage drop measured over that 0.1 ohm shunt resistor. I'm measuring it on channel 2, and you can see channel 2 is set to 100 millivolts per division. So let's just measure that voltage range over there. We want to measure voltage. There you can see the voltage difference there, the delta V, is 156 millivolts on channel 2, and this is without the bypass capacitors active, by the way. And you can see it's drawing a significant amount of current of course being calculated by the voltage over the resistance, so 156 millivolts over 0.1 ohms. That gives you about 1.5 amps current draw. Right, that might sound like a lot of current being drawn, but you must keep in mind that it is for a very, very short period. If we zoom in there on the horizontal scale, you can see we're at 250 nanoseconds per division, right? So that's basically the length of that pulse over there, and it's really for a short period that current is being drawn. Okay, so let's just go back here, and what I'm going to do now is put back the 47 microfarad capacitor. Oops, here we go, and you can see it's almost completely filtered out that bump that we had there. There's still a small bump left there. So basically what's happening now is the current is being drawn from the 47 microfarad capacitor. It's acting as a reservoir, and let's add back the 0.1 microfarad capacitor. Oops, there we go, and you can see it's effectively filtered out almost all the current draw from the main power supply. Everything is being drawn from the capacitors for that very short period, and then you can see also now what the importance is of having filter capacitors on your circuit, not only for your 555 timer chips, but also for other chips. especially on the transistorized versions of these chips, with the positive and negative going edges, you will see current spikes. Well, thanks guys. I hope you found that informative. See you next time.